So far, in this program on steam power, we have examined steam production and the different types of boilers and fossil fuels which are used for this purpose.
We are now going to shift the focus onto steam utilization by taking a detailed look at the steam turbine which drives the electrical generator. We already studied the various turbine cycles and factors affecting efficiency at the beginning of this program. In this module, we'll look at the main features of turbine construction, including the various components and support systems such as gland steam, lube and hydraulic oil, and the condenser. The subject of turbine operation, control, and protection will be dealt with in the next module. The steam turbine is certainly one of the most popular prime movers, especially for driving large power generators. The size of steam turbines built and installed runs all the way from about 5 megawatts up to 1,000 megawatts or more. So what is it that makes the steam turbine the preferred prime mover in comparison with, say, the diesel engine? Well, there are quite a number of advantages, the main factor being that of physical size. For example, a 30 megawatt steam turbine is probably smaller than a 5 megawatt diesel. Another advantage is that the steam turbine is far less complicated and contains very few moving parts. The moving parts are the rotor, which drives the generator, and the steam control valves and control gear. The amount of vibration produced by a steam turbine generator and transmitted to the surrounding area is relatively low, provided, of course, that the machine is in good condition and is correctly installed and aligned. This makes for a quieter operating plant, particularly when compared with the diesel engine or even the gas turbine. The steam turbine runs at high speed, usually 3,600 RPM in North America or 3,000 RPM in Europe, and can therefore be coupled directly to a two-pole generator. Remembering that the diesel engine operates at around 200 RPM, we can see one of the reasons why the specific output of the steam turbine is much greater. One other advantageous factor is the relative ease of controlling the output of the steam turbine. This is achieved simply by adjusting the amount of steam admitted to and flowing through the turbine. As we'll see later, admission valves, also known as control valves, are installed for this purpose. The turbine stop valve, or valves, is located upstream of the control valves. In case of an emergency, the stop valve closes automatically, cutting off all steam supply to the turbine and bringing the machine to a halt. This sketch shows us the major components of a 150 megawatt reheat turbine. We see here the rotor and the inner and outer casing or shell. This casing surrounds the rotor, leaving very fine clearances between the stationary and moving parts. The objective of the inner casing is to direct the steam through the turbine. The inner casing is fitted into the upper and lower half of the outer shell, which in turn is supported on a heavy reinforced concrete base. The base must be firm enough to ensure rigidity. That is, it must permit no movement in the vertical plane which could upset the alignment of the machine. The support bearings are allowed restricted movement in the axial plane to cope with expansion of the turbine, as we shall see later. Other components noticeable here are the governor pedestal, which supports the front end bearing, and the governor system. In this particular machine, steam from the stop valve is fed into steam chests located on either side of the turbine. The turbine admission valves are located in each steam chest to control the flow of steam into the turbine. The turbine rotor is directly coupled to the generator rotor to transfer the mechanical energy produced in the turbine to the generator, where it is converted into electrical energy. Now, as we progress through this module, we'll be discussing the function of all of these components and many others. At this point, we're mainly concerned with identifying these items. Make sure that you know where the following components are located on your particular turbines: the turbine outer casing, the generator, the turbine rotor, the generator rotor, and the associated coupling, the governor pedestal, the main steam stop valves, the steam chest and associated admission valves or control valves, the location of bearings which support the turbine rotor. Now, the particular machine that we've been studying is made up of several cylinders, and we'll be looking at other cylinder arrangements in a moment. But first, let's take a closer look at a single cylinder machine in order to help us understand the principles of turbine operation, how it actually functions and produces power. As we all know, steam at high pressure and temperature, say 1800 psi and 1000 degrees Fahrenheit, is admitted at one end of the turbine. After passing through the turbine, this steam exits at a much lower pressure and temperature, say 50 psia and 250 degrees Fahrenheit for a typical back pressure turbine. However, if the turbine is of the condensing type, and this is far more common, then the steam exiting from the turbine will be at a pressure far below atmospheric, say 1 psia, and at a temperature of about 100 degrees Fahrenheit. Clearly, the amount of energy in the steam exhausted from the turbine is much less than in the steam entering the turbine. The heat energy has been used to force the turbine rotor to rotate at high speed and consequently produce mechanical energy. But how does it do this? Well, the simple answer is that the turbine blades are designed to take advantage of the decrease in steam pressure and consequent increase in steam velocity. As we know, the heart of the turbine, the bit that makes it work, is the relationship between the fixed and moving blades. The fixed blades guide the steam onto the moving blades. As the steam passes through the moving blades, it causes the disc to which they are attached to rotate, and consequently the shaft rotates. Each pair of stationary and associated moving blades are known as one stage. Most steam turbines contain many stages of blading. In this example of a single-cylinder machine shown here, we have 7 stages. And do not forget the stationary blade is always ahead of the moving blade. Actually, each pair of stationary blades is shaped to form a convergent divergent nozzle. However, the form of the nozzle is bent to receive the steam exiting from the previous moving stage and then to turn and redirect the steam onto the next moving stage. Now, before you raise the question, but what about impulse and reaction type blading? Let me say that in practice, when you're operating a turbine, it's not vitally important whether the blading is impulse or reaction. This is really a design and construction feature. However, it will certainly be worth our while to take a look at this subject, as the type of blading used does affect other structural features. Let's first examine impulse blading. As the steam passes through the first row of stationary blades or nozzles, its pressure decreases, and as a result, the steam velocity increases. These changes are plotted on this graph. As this high-velocity steam is directed onto the moving blade, the impulse pushes the blade forward and consequently produces rotation of the shaft. By the time the steam leaves the moving blade, it has lost much of its velocity, and it then passes on through the next row of stationary blades. Again, the pressure falls and the velocity increases due to expansion of the steam, and once again this is directed onto the next row of moving blades, and so on. We can see that as a result of pressure drop, the velocity of the steam increases each time it passes through a set of stationary blades, but the velocity then decreases as the steam passes through the moving blades and gives up energy. Eventually, When the pressure has fallen to a low value, it can no longer expand and produce work, and it is exhausted from the turbine. But look what happens here to the pressure as the steam passes through the moving blades. It does not decrease, neither does it increase. In fact, the pressure across the moving blades remains the same. It is the change in velocity which actually does the work and provides the energy to drive the turbine. This feature of impulse blading, that is, constant pressure across the moving stage, brings about a certain constructional advantage. As there is no pressure drop, there is no tendency for steam to leak around the outside circumference of the blades. Because of this feature, we will inevitably find that impulse blading is used in the high-pressure stages of the turbine. In fact, you'll often see large holes bored through the wheel or disc in the higher pressure stages. This is done to ensure that there is no pressure differential across the wheel, and so maintain the correct impulse characteristic of the moving blades. Now let's move on to look at the characteristics of reaction-type blading. In this case, the mechanical force on the blade is caused by reaction as the jet of steam exits from the blade. This is the same concept as a jet engine. With this type of blading, the moving blades are shaped in the same manner as the fixed blade, that is, in the profile of a curved nozzle. This causes the steam pressure to fall as it passes through the moving blade, resulting in an expansion of the steam and an increase in its velocity relative to the blade, causing a powerful jet action. As before, the exiting steam then passes into the next stage of fixed blades, where it is again expanded and redirected to enter the next set of moving blades. So you can see that in this type of blading, the pressure decreases as the steam passes through both the moving blades and the stationary blading. Although the reaction turbine is efficient in its use of heat, there is always the potential for some losses due to steam leaking around the periphery of the moving blades, especially in the high-pressure section. In order to reduce this tendency, a reaction turbine will normally have many more stages so that the pressure drop in each stage is lower. Consequently, the machine will be physically longer. In practice, a compromise is reached, and today most turbines combine both types, using impulse blading in the high-pressure stages and reaction blading in the low-pressure stages. Now, at this point, it's time we all took a break, and then we'll come back and look more closely at features of turbine construction. For now, please switch off the tape and review this material in your workbook. I'm sure we all remember the old trick question, what weighs more, 1 ton of feathers or 1 ton of lead? Well, of course, both of these quantities weigh the same. We have just said so, 1 ton. But there is no doubt that the volume of feathers would be much, much greater than that of lead. In other words, the specific volume of feathers in cubic meters per kilogram or cubic feet per pound is much greater than that of lead. This problem of specific volume is of concern to us when we consider the steam passing through the turbine. We know that the steam pressure falls, and consequently its volume must increase as it approaches the low-pressure end. In fact, the change in specific volume of steam is quite dramatic, as we can see in this table. 1 pound of steam at 2,500 psia and 1,050 degrees Fahrenheit occupies a space of 1/3 of a cubic foot. At 500 psia and 500 degrees Fahrenheit, the specific volume is 1 cubic foot. At atmospheric conditions, the volume occupied by 1 pound of steam is 27 cubic feet. And in the case of a condensing turbine, where we have steam exhausting at, say, 1 psia, the specific volume is 333 cubic feet per pound. So one clear consequence of this is that we have to make the casing continuously bigger as we move from the high pressure to the low pressure end. This is very evident to the eye when we look at this single-cylinder turbine. But notice, it is not only the casing that must be made bigger, but the turbine blades must also be larger in order to utilize this low-pressure steam. On turbines of high output, say above 100 megawatts, it becomes physically difficult to make the cylinder large enough to accommodate all of the low-pressure steam. To get over this problem, multi-cylinder arrangements are used, and let's look at some of these arrangements. Here we see a common arrangement of two cylinders which may be used for units of up to about 150 megawatts. Crossover pipes are used to connect the exhaust from the high-pressure cylinder to the inlet of the low-pressure cylinder. Most low-pressure cylinders are of the double flow type, where steam enters at the center and flows outwards in opposite directions. This provides some balance to the thrust and tends to keep the shaft centered. As the steam path of the high-pressure and low-pressure cylinders is in series, all of the control is carried out at the steam inlet admission valves at the high-pressure end. The next development from this two-cylinder arrangement introduces reheat and the addition of the intermediate pressure stage of the turbine. A very common arrangement for reheat turbines up to about 250 megawatts is shown here. The high pressure and intermediate pressure cylinders are combined in one casing. But of course the steam path is quite separate. Note that the concept of counterflow is also used here, with the steam flowing through the high pressure cylinder in the opposite direction to that of the intermediate pressure cylinder to help produce a balanced thrust. As turbines become bigger and bigger, it is necessary to add yet further cylinders, and the arrangement shown here is typical for machines in the 500 to 600 megawatt range. As you can see, we have separate high pressure and intermediate pressure cylinders, and also it has become necessary to add a further low pressure cylinder in order to handle the high volume of steam. With all of the configurations shown, the general control of steam flow through the turbine is achieved by adjusting the admission valves at the high pressure inlet. However, note that with reheat units, additional control valves, known as intercept valves, are fitted at the inlet to the intermediate pressure cylinder for protection purposes. We'll be discussing this in detail when we look at control and protection in the next module in this series. Yet another cylinder arrangement used on earlier reheat machines is known as the cross-compound system, shown here. It really consists of two separate turbines, each coupled to their own generator, but interlocked through a common steam system. The high pressure and intermediate pressure cylinders drive one generator, while the two low pressure cylinders drive the other. Again, the steam flow through the combined turbine is controlled at the high pressure inlet, thus controlling the output of both generators. Of course, the large reheat units that we have been considering would typically be found in central power stations of large utility companies. More recent installations, particularly in industrial situations, are likely to be smaller units, probably within the range of 60 to 150 megawatts. In order to examine some of the basic construction features, let's take a look at this single-cylinder machine. Steam is supplied to the steam chest from the boiler after passing through the turbine stop valve. The amount of steam passing through the turbine is regulated by adjustment of steam admission valves. This in turn controls the output of the turbine and the coupled generator. At various stages along the steam path, steam is extracted from the turbine. This extraction steam is commonly used for feed water heating, but there may be other applications as well. The concept is that the extracted steam is put to good use after performing some work in the turbine. You will remember that we discussed this in the first tape in this series when we looked at efficiency. The turbine rotor is supported on journal bearings which are located at each end of the cylinder. It is essential that these bearings retain their correct alignment, as the clearances between the rotating parts and the fixed parts of the machine are extremely small. A thrust bearing is located along with the journal bearing at the governor pedestal in order to locate the shaft and prevent movement in the axial direction. What do we mean by this? Well, in this single-cylinder arrangement, the flow of steam through the turbine tends to push the rotor towards the generator. If this thrust was not contained, the rotating blades could conceivably come into contact with the stationary blades of the next stage and cause quite a catastrophe. To prevent this occurrence, a fixed collar on the shaft is held in position by lubricated thrust pads. During construction and maintenance of the machine, these pads are carefully set to ensure that the correct clearances exist between rotating and stationary parts. Allowance must be made for the casing to expand as it becomes heated by the steam flow. In a single-cylinder machine like this, the normal method is to anchor the machine solidly at the low-pressure end, that is, at the turbine exhaust, and allow the front end pedestal to move forwards. In large machines, the expansion in this longitudinal direction may be over 1 inch, that is, 25 millimeters. In this particular machine, the pedestal is fixed to a flexible support which allows the movement to take place. A more common arrangement on larger machines is to fit the base of the pedestal with sliding feet to allow free movement in the axial direction. Now let's take a close look at a typical rotor. Moving from the front end to the rear, we see first the thrust collar, which bears against the thrust pads during operation. Just ahead of this, there is the portion of the shaft which sits in the journal bearing. This area should be perfectly smooth with no indentations or marks. Moving further along, we come to the gland seals, which are needed to reduce steam leakage along the shaft. We'll be talking about this arrangement in more detail later. We now come to the series of wheels, or discs as they are known, which extend along the length of the shaft. Blades are fitted all around the periphery of the discs and are held firmly in place at the roots. On many machines, further support is provided by fitting rings or shrouds around the outside of the blading. Note the much larger size of the low-pressure blades in order to handle the increased volume of steam at this end. Now, continuing our examination along the length of the rotor, we come to the low-pressure end gland seal. This is at the interface between the casing and the rotor. Just on the outside of the casing is fitted the low-pressure end journal bearing. At the very end of the shaft, we find the coupling, which is used to join the turbine and generator rotors. In addition, at this end of the shaft, we will often find a large gear drive, which engages with the turning gear. As we'll see later, the turning gear allows us to rotate the rotor at very low speed, say 1 RPM, without having steam pass through the machine. This is used during shutdown to ensure even cooling and so prevent distortion of the rotor. More about this later. In earlier machines, the discs are shrunk onto the rotor shaft. A problem with this type of construction is that in some cases, steam may leak along the shaft and cause distortion due to differential heating as well as a loss of efficiency. To overcome this problem, in modern turbines, the discs in the shaft are forged in one piece and then machined. Yet another method of building up the rotor is by welding discs together and so eliminating the shaft. Now remember that in between each disc and associated blades, we have to fit the stationary blades. Let's see how these are held in place. The first time we examine a turbine, we might imagine that these stationary blades could be fixed to the outer casing to line up with the moving blades, like this. But we do have a problem with this arrangement. What is there to stop the steam passing around the blade instead of through it? In order to prevent this, a shield known as a diaphragm is constructed, extending all the way from the inner diameter of the stationary blade down to the shaft, leaving a small clearance to allow rotation. In practice, the stationary blades are inserted into the diaphragm like this, and the diaphragm itself is fixed into the turbine casing. When diaphragms are removed during maintenance periods, they look like this. And here is a view of the bottom half of a turbine casing with the diaphragms in place. The diaphragms are sized to leave a small inside clearance to allow the shaft to rotate. Seal strips are fitted at this location to prevent steam leakage. After all, we want all steam to pass through the blading, not around it. And we'll be talking about steam seals later. When the turbine is assembled, the rotor must be very carefully lowered into place so that the discs fit perfectly between the respective diaphragms. Once the rotor is in place, the axial clearance can be adjusted and finally fixed in place at the thrust bearing. Similarly, the journal bearings must be adjusted to provide correct alignment with the generator rotor. When all adjustments are complete, the top half of the casing, which is a mirror image of the bottom part, is very carefully lowered into place and finally bolted down. The exterior of the turbine casing must be very well insulated to prevent heat loss. With temperatures at the high pressure end in the region of 1,000 degrees Fahrenheit, we could suffer a considerable loss of efficiency as well as an uncomfortable turbine room if the insulation was inadequate. Now, in this segment, we've looked at general features of turbine construction. Using this information as a guide, make sure that you check and learn the structural features of your own turbines. At this point, it's time for a break, so please switch off the tape now and review this material in your workbook. We've mentioned several times the terms gland seals and steam sealing strips. It's time for us to take a closer look at these. When we consider that the rotor is turning at high speed, it is obvious that some clearance must be provided for the shaft as it protrudes from the stationary casing at each end of the turbine. Now remember, there is very hot steam at substantial pressure inside the casing at the high pressure end of the machine. So there is the potential for a considerable amount of this hot steam to leak out through the space between the rotating shaft and the casing. And would we not have the same condition at the low pressure end? Well, yes, if this is a back pressure turbine with a positive exhaust pressure at, say, 50 psi or over. Although the pressure and temperature is less, there would still be leakage between the casing and the rotating shaft. But what about the case of a condensing turbine? Well, in this situation, there is a vacuum inside the casing at the low pressure end. So instead of steam leaking out, air would leak in, and we do not like that either. It could lead to a loss of vacuum and consequent loss of efficiency. In order to reduce this leakage as far as possible, gland seals are located at each end of the casing. The aim of the seal is to provide a high resistance to the flow of steam or air. This is achieved by the use of a labyrinth seal. The rotating portion on the shaft is slotted like this, while the stationary portion consists of thin metallic strips which are pressed into the rotating grooves by very light spring pressure. The resultant labyrinth path considerably reduces the leakage of steam out or air in. Even so, there will still be some leakage of steam at the high pressure end through the gland seal. This leakage steam is extracted from the gland and fed into a low-pressure extraction point. The leak-off valve automatically adjusts the pressure within the gland steam header to maintain approximately 5 psig. But even at that low pressure, there will still be some leakage along the shaft into the turbine room. In order to prevent this steam from getting into the turbine room, it is drawn from the outside of the gland seal by a slight vacuum, which is produced by the gland steam exhauster. Some heat is recovered from this small amount of steam, bypassing it through a heat exchanger in the condensate system known as the gland steam condenser. Now let's see what's happening at the vacuum end of the turbine. Well, we definitely do not want air to enter the casing, even the small amount that may flow across the labyrinth seal. In order to prevent the leakage of air into the casing, low-pressure steam is provided from the header to the low-pressure gland seal. This results in a small amount of steam entering the turbine casing, and this is far preferable to air. Of course, some of the steam will also try to pass along the shaft in the opposite direction to atmosphere. But this is captured by the gland steam exhauster in the same manner as for the high-pressure gland seal. So we can see that leak-off steam from the high-pressure end is useful in providing sealing steam at the low-pressure end. As the load changes, the leak-off valve opening adjusts to maintain the appropriate header pressure.
But how does the system work when we're preparing for startup? In this situation, we need to pull a vacuum in the turbine and condenser before admitting any steam into the turbine. So in this condition, we have no leak-off steam.
Instead, live steam is supplied to the gland steam header. The live steam supply valve is set to control the header pressure at about 3 psi to coordinate its operation with the leak-off valve. When the turbine comes on load, the leak-off steam from the high-pressure gland feeds into the header and so raises its pressure. When the pressure gets to 3 psi, the live steam supply valve will close. When the pressure rises to 5 psi, the leak-off valve will open enough to maintain this pressure.
Remember that there are two basic circuits in the gland steam seal system.
First, the gland steam header, which supplies steam to the seals or dumps excess steam. The second circuit extracts leakage steam from the extremities of the glands and passes it through a heat exchanger and the gland steam exhauster. Make sure to check and learn details of your own gland steam system.
Sealing strips are similarly used in other parts of the turbine where we need to eliminate or at least reduce steam leakage.
A typical example is the interstage seals, which are fitted at the inner circumference of the diaphragms where the shaft rotates. In all cases, the seal strips are made of very thin, soft, metallic material. They rub on the shaft and reduce the leakage as much as possible. Of course, as time passes, the sealing strips wear and need to be replaced during regular maintenance. We'll be discussing this aspect in another module in this series.
Well, so much for sealing systems. Another very important support system that is essential for turbine operation is that of lube oil and hydraulic oil supply. Let's look at the lubricating oil system first.
A continuous flow of lube oil must be circulated through all of the turbine and generator bearings. Typically, the arrangement would look like this for a single-cylinder machine. The lube oil supply header is maintained at about 50 psi, and from here the oil is force-fed through each of the bearings, including the turbine thrust bearing. After passing through the bearings, the oil flows into the return header, and from there to the lube oil tank. The lube oil is pumped from this tank in order to feed the supply header. So we have, in effect, a closed cycle.
But there are some other important features. First, the need for cooling.
As the lube oil passes through the bearings, it picks up heat and its temperature rises, conducting heat away from the bearings. The effect of this would be to continuously raise the temperature of the oil in the tank. In order to prevent this, a cooler is provided, and this is usually placed in the path of the lube oil supply. The lube oil cooler is usually of the tube and shell type, with cooling water passing through the inside of the tubes. It is normal to fit two coolers so that one may be taken out of service for cleaning at any time. Thus, the change can be accomplished without interrupting the supply of oil. Actually, the raising of lube oil temperature in the tank has a slight advantage in that it allows any moisture contained in the oil to vaporize. For this reason, a vapor extractor is fitted to the top of the tank to draw off any vapor and discharge it to atmosphere. But where does the moisture come from? Well, this may be picked up by the oil in its passage through the bearings with their proximity to the gland steam. The vapor extractor will also remove any traces of hydrogen that may infiltrate the lube oil from the generator cooling system. The subject of hydrogen cooling and its associated seal oil system is discussed in the power generation module of this program.
More serious yet, the oil is likely to pick up fine pieces of metal and other contaminants in its route through the system. And these contaminants could cause serious damage to the bearings and therefore must be removed.
Most lube oil systems include a filtering system within the circuit. This may consist of bag-type filters within the oil tank, or external cartridge filters, or a centrifuge which continuously circulates oil from and back to the tank. Maintaining the cleanliness and purity of the oil is extremely important to good turbine operation. Usually, the lube oil is sampled at regular intervals, say monthly or bi-monthly, and analyzed for impurities and other characteristics. The supply of lube oil is so vital to the operation of the turbine and generator that a standby pump must always be provided and maintained ready for startup on automatic control.
But one question comes to mind. What would happen in the case that we lost all auxiliary AC power? This could happen, for example, in the case of a turbine generator trip in a facility with no station service backup. We'd then be faced with the prospect of the turbine generator running down without the circulation of lube oil, a condition that could conceivably damage all of the bearings.
In order to prevent this potential disaster, many machines are equipped with a DC oil pump, which would be fed from the station battery in such an emergency.
Now let's move on to look at the hydraulic oil system. This system operates at a much higher pressure than the lube oil system, even as high as 2,000 psi in some machines. Fireproof synthetic oil is often used as a safety feature. But what is the purpose of this hydraulic system?
Well, the high-pressure oil is used as the medium for operating the turbine control system. For example, the servo mechanism, which provides the force to adjust the turbine admission valves, is motivated by hydraulic oil, hence the high pressure needed. Hydraulic oil is also used to hold open the turbine stop valve during operation and hold open the extraction line non-return valves during normal operation. Hydraulic oil is employed to provide a relatively large force in response to a small signal from the control system. For example, the servo mechanism that we just mentioned is really a power amplifier that responds to a small movement and force of, say, a few pounds from the governor system, and turns this into a force of several tons to operate the turbine valves against the high-pressure steam. In this simplified example shown here, the turbine steam control valve is adjusted by the position of the hydraulic servo piston. This large system is controlled by the small pilot valve here. Now, suppose the governor control system lifts the operating lever slightly. As we can see, this will now allow high-pressure oil to enter the servo cylinder above the piston. At the same time, it will allow oil below the piston to pass to the oil drain. In response to this, the piston will be forced downwards, partially closing the control valve. But look, this movement downward also moves the operating lever, and this moves the pilot valve downward, so closing off the servo cylinder, which is now in a new position.
We'll be looking in much more detail at the turbine control system in the next module in this series. For now, we're just looking at applications for hydraulic oil. In many turbines, the same grade of oil is used for both applications, so the hydraulic and lube oil systems are combined to utilize the same oil tank and the same pumps.
The main oil pump is mounted in the front end pedestal and is driven directly from the turbine shaft. Diagrammatically, the scheme looks like this. When the machine is in operation, the main oil pump here delivers oil at 250 psi. This supplies the hydraulic oil system. At the same time, it provides oil to the lube oil header at 50 psi through a reducing valve. During startup and shutdown, a motor-driven high-pressure oil pump is used. Again, this supplies both the hydraulic oil system and the lube oil system. In this arrangement, this pump is known as the auxiliary oil pump, since it is the main standby to the shaft-driven pump. When the turbine is out of service and operating on turning gear, we still need to provide lubrication to the bearings. However, in this situation, with hydraulic oil not required, it would be inefficient to run the large auxiliary oil pump. Instead, a small pump is installed known as the turning gear oil pump, and this provides sufficient oil for lubrication only. And as before, there is a DC emergency pump which will provide lubrication in the case that all AC service supply power is lost. So we can see that there is in fact a hierarchy of oil pumps with automatic startup based on pressure readings. If the high pressure oil pump fails and the pressure falls, the AC auxiliary oil pump will cut in automatically. If the lube oil pressure falls, the turning gear oil pump starts up automatically. And if this consequently fails, the DC oil pump will start. As with all automatic devices, the pump auto start operations should be checked on all pumps regularly. Make sure that you check out the details of your own lube oil and hydraulic oil systems. You should be thoroughly familiar with the location of all pumps and controls for these pumps.
Now at this point, let's take a break, and then we'll come back and take a look at vacuum equipment on the turbine. For now, please switch off the tape and review this material in your workbook. An important part of operating a condensing turbine installation is the maintenance of correct vacuum in the condenser. Commonly, the condenser is located below the exhaust end of the turbine, but there are other configurations. In the scheme shown here, the condenser is fitted directly at the tail end of the turbine on the same level. Another arrangement, known as a pannier condenser, consists of two vessels located at the same level, one on either side of the exhaust. As we already pointed out in an earlier module, a vacuum is formed when steam exhausting from the turbine is cooled and condensed back into water. The dramatic change in volume from steam to water leaves a large empty space, and as the condenser is a closed vessel, the result is a vacuum. The actual pressure in the steam space of the condenser and correspondingly at the turbine exhaust will be about 1 to 2 psia, depending on actual local conditions. The steam space in the condenser is filled with low-pressure steam exhausted from the turbine, which quickly turns to water droplets as it comes into contact with the outside surface of the cooling tubes. Most condensers contain several thousand tubes about 1 inch in diameter, usually made of non-corrosive metals such as copper and nickel, brass, and even stainless steel. Cooling water passes through the inside of these tubes, while steam condenses on the outside of the tubes. This so-called condensate then falls to the bottom of the condenser, where it is collected in a vessel known as the hot well. From here, the condensate is removed by the condensate pump and circulated back to the system. In order to condense steam into water, all of the latent heat must be removed. That is about 970 BTU per pound. In order to achieve this, a very large quantity of cooling water is required. For example, a 60 megawatt unit may require as much as 35,800 GPM of cooling water to pass through the condenser. Such a large quantity of water cannot be supplied by a water treatment system. Therefore, the condenser cooling water, or circulating water as it is known, is normally taken from a nearby river or lake or even the sea. In some cases, a closed circuit system is installed using a cooling tower. We'll be talking more about the actual circulating water system and its components later in this program. For now, we're concerned with the condenser and other vacuum equipment. In the arrangement shown here, the circulating water enters at one end of the condenser, filling the inlet water box.
then passes through the tubes into the outlet water box. From here, the water circulates back to the system. This particular arrangement is known as a single-pass system. In many installations, a double-pass condenser is used. Here, the water enters at the bottom, passes through the lower tubes, arrives at the far water box, and then is circulated back through the upper set of tubes, exiting from the upper water box. Over a period of time, the circulating water may leave some deposits inside the tubes. The consequence of this is a reduction in heat transfer and a rise in the back pressure inside the condenser. This results in a loss of efficiency and lower output from the turbine. The circulating water may also deposit algae, mussels, and other marine life on the front of the tube plate, reducing the flow of water through the tubes. Again, the result is a loss in cooling and a consequent rise in back pressure. Generally, the condenser needs to be cleaned manually from time to time, and in most cases, this entails shutting down the turbine. There are, however, some machines which are designed to allow one half of the condenser to be cleaned, while the other half remains in service, and the unit continues operating at reduced load. In an attempt to maintain a clean condenser, chemical injection is carried out at some installations. Adding a biocide to the circulating water can reduce or eliminate the growth of algae. Sulfuric acid may also be added in some plants where a closed-cycle cooling tower system is used. The objective is to lower the pH slightly to about 6.5 in an attempt to prevent scale forming inside the tubes. Another chemical used on closed-cycle systems acts as a dispersant with the aim of keeping solids in suspension and preventing deposits from forming on the inside tube surface. Many condensers are fitted with a siphon connection on top of the water box. The objective of this vacuum connection is to ensure that the water boxes remain completely full of water so that all of the cooling tubes remain effective. But how could it be otherwise? Well, the circulating water will likely contain air bubbles which may be released at the top of the water box, forming a large air pocket. In time, as the air pocket increases, the level of the water at the top of the water box falls, and consequently there will be no water flow through some of the tubes. The result of this reduction in heat exchange will be that the condenser is less effective and the turbine back pressure increases. The siphon connection prevents this from happening by drawing off the air at the top of the water box and piping this into a vacuum tank. The vacuum in the tank is maintained at about 25 inches of mercury by small vacuum pumps that are intermittently operated. A water level sensor in the water box operates a control valve on the siphon connection. When the level falls below a set level, the valve opens and air is drawn out, allowing the water level to rise. When the level raises to fill the water box, the control valve closes.
The problem of air accumulation may also occur inside the steam space of the condenser. Remember that this area operates under a negative pressure, a vacuum.
Therefore, any leakage by valves, piping, or flanges will allow air to leak into the steam space of the condenser instead of steam leaking out. Also, some incondensable gases, such as oxygen and carbon dioxide, may be released from the steam as it condenses. There is a tendency for these gases, plus any small amount of leakage air, to accumulate inside the steam space and eventually cause the back pressure to rise, reducing turbine efficiency. In order to remove air and gases from the steam space, vacuum devices are fitted, such as a steam ejector and a vacuum pump. This air removal equipment is connected to a specific location in the condenser known as the air box. In this area, additional cooling tubes are concentrated to ensure that the steam condenses and only air and gases are removed. In many plants, the discharge from the vacuum equipment is monitored to provide a measure of air leakage into the condenser. During normal operation, this air leakage should be quite small. In fact, a good test of this during operation is to shut down the vacuum pump or steam ejector and observe the rate at which the back pressure increases. This should be quite slow, say 1 inch of mercury in about 30 minutes. Compare this with the change which would take place if all of the circulating water flow were to cease, perhaps due to a trip of the circulating water pumps. In this case, with no condensing taking place at all, the back pressure would rise immediately, and the turbine would have to be tripped.
In practice, this takes place automatically. And we'll be discussing this when we look at protection devices in the next module. So we can see that during normal operation, the vacuum equipment is intended to maintain the vacuum in the condenser, not to create it. However, we also depend upon the vacuum equipment to draw a vacuum before startup.
In this situation, before steam is admitted to the turbine, the condenser and the turbine are full of air. In order to remove this air, the vacuum pump or steam ejector must be placed in service and so pull a vacuum inside the unit. Let's see how the steam ejector works. This functions on the principle of the Venturi nozzle, like this. When high-velocity steam passes through this nozzle, it creates a vacuum at this convergent point. This is the point which is connected to the air box in the condenser. The air enters the nozzle and is mixed with the steam passing through. On a startup ejector, also known as a hogging ejector, this mixture is discharged to atmosphere. However, the requirement for air removal when the turbine is in service is much less. Therefore, the on-load ejector uses smaller nozzles and has some heat and steam recovery. As before, air is drawn from the condenser by the primary ejector, and the air and steam mixture discharges into a heat exchanger to condense the steam. The cooling medium is usually condensate, so all of the heat is retained within the cycle from the intercooler. The air is now drawn into a second stage ejector, which is at quite low pressure, that is, a modest vacuum. From here, the air and a small amount of steam is exhausted to atmosphere.
The creation and maintenance of vacuum in the condenser is an exceedingly important part of turbine operation. And we'll be looking at this in more detail in the next module in this series, when we focus our attention on turbine operation and control. Make sure that you learn all of the features of the condenser and vacuum equipment which is installed in your plant.